All right, guys, we're going to go through just quick reminders about some of the things we've done with waves. With us having like long break and stuff, I know sometimes we forget. So you have two basic types of wave. So here's my midline, my median line. If there's not a wave, first type of wave, it's going to look like that. Okay. This is a transverse wave. Okay. When I say transverse, if the wave motion, the wave is going this way. Okay. A particle like that one is going up and down. So transverse. So it's going to be perpendicular or a right angle. So if you had this dot here, as a wave travels through, it goes up and down. As a wave travels through this, it goes up and down. Wave travels right here, it goes up and down. All right, we're going to talk about the other wave, which has a different type of motion in a second, and you'll kind of see the difference. On a transverse wave, the top, crest, bottom, trough. From the top of the top to the midline, or the midline to the bottom most part, are both referred to as the amplitude. So it's kind of like the wave height or depth. And then a wavelength is going to be one whole wave cycle. So you have to have a crest and a trough. So that is one wave. So the wavelength, then therefore, would be that. And you could also say that it would be from here, this point, to this point. Which in an ideal world, if I could draw my waves perfect, would be the same. Whether or not those actually measure out to be very unlikely, that is a defect on my drawing, not on a wave. You can measure frequency. Which is going to be like the number of waves over the time given. So this has one wave, two waves. We're going to say that it kind of continues. Again, my drawing, right? So this is two waves. Let's say this occurs over a period of 10 seconds. It's an arbitrary, I just made it up. Your frequency would be 2 over 10, which is 0.2. Your period is how many waves a second. And the easiest way to do that is to go 1 over frequency, which means 1 over 0.2, which would be 5. All right, the other type of wave is a longitudinal. Longitudinal wave think of like that, parallel. So I'm not super great at drawing these straight. See, it gets smaller. That is a me problem, not a wave problem. Okay, so you have compression where they are tightly spaced next to each other. You have rarefaction where they're more spread out. And in this case, your wavelength would be between your compressions. Again, sorry, this is a drawing thing, not a wave thing, but I think you get the picture. Sound is a longitudinal wave, which is why sometimes when we draw it, we see it like this. You can see how that could be very similar type of thing. I'm sorry. Oh, and that's what I wanted to say. The motion of are parallel. So if there's an object right here, and let's here, my wave is moving this way, my object is moving like this. So the object's motion and the wave motion are parallel. So in this case, I drew them up and down, which would be the same thing if my wave was going like this. You get the picture. They're parallel. You have the velocity of the wave is equal to the frequency of the wave times the wavelength. That frequency is measured in hertz. Wavelength is going to be in meters. Velocity is going to be in meters per second unless it's otherwise stated. So you could see something where like light has 3 times 10 to the 8th meters per second velocity is equal to 15,000 hertz. Find the wavelength, and I'm making these numbers up, but you would go 3 times 10 to the 8th divided by 15 would be 20,000 meters, which is a crazy big number, but that's because that's a very small frequency for such a big velocity. Again, this is just a consequence of me making it up for the sake of examples. All right, so this is sound. Remember, sound cannot travel in space. If there's an explosion in space, that's Saturn, sound cannot travel. Okay, if there's just none. Light can travel in space. Light is a special type of wave we're going to talk about next time, but it does not need a medium. Sound needs a medium. In fact, you have liquid, gas, and solid. Sound actually travels the best through the solid, then liquid, then gas. So if there's a stampede coming, you can actually pick up the vibrations on the ground before you can hear them through the air. When something's flying through the air and it's faster, than sound, which is around 340 meters per second, what you create with that high pressure is a sonic boom. You're going to hear it. It produces a shock wave. All right, let's talk about some wave behavior. And we're just going to cover the basics. Resonance. What you're going to hear is natural frequency a lot. These are your tuning forks. This is your opera singer in the shattering of the glass, that kind of thing. Reflection. You're going to hear bounces. This is a reflection in the mirror. This is an echo or sonar or any of that stuff. That is reflection. It's hits something and strikes off. Hits something and it strikes off. We have diffraction. That's when your wave kind of bends around barriers. So if you have a barrier, your waves are approaching it and go through. See that. You're going to see them go through. If the barrier was smaller, you see more of a bend, hopefully an equal bend, but still one. And then refraction. That is your bending because of a change in mediums. That is your straw in your cup of water. That's because it's going from air to water, and it's going to change kind of those wave behaviors, and it results in something being slightly off when you look through it. This is also if you had like a little crystal. My grandmother had them on her chain pulleys on her lights, and it was just a little clear crystal prism thing. And what happened when the sunlight hit it is it would reflect all the colors of the rainbow, make like a little prism on the ground. That is also refraction. The other one would be the Doppler effect, which we did that lab over. Remember, if something's coming towards you, you hear a higher frequency. If something's going away from you, it means you're going to hear a lower pitch because of that lower frequency. Remember, we put the car in the middle of those rings. So if he was going this way, those rings kind of came together, and you wouldn't have heard, but you saw frequency increase towards the spot. When you're looking at two waves and they're going to interfere with one another, a wave like this, a wave like this. If this one is +4 high and this one's -1 high, the resulting wave would be +3 high. So they're going to add up. If you have one that is +1, +1, you would have one +2. Deconstructive, constructive. To construct something means to build it up. Destruct something means to tear it down. The only last hint I could possibly have for you at this point is sonar, echo, location, anything. Let's say I have a bat, and we did 2 of these warm-ups. There's my bat. Obviously, I don't even have to tell you about it. It's obviously a bat. And my bat is trying to find food. Okay. and it hits the sound the bat is producing, hits the moth, and then bounces back up to the bat's ears, and that whole time frame is, let's say, 0.02 seconds, and you have the velocity of that wave, and you want to know the distance. So let's say the velocity that he's, and I have no idea what let's say it's like 5 meters per second, and it's totally not. I just don't know off the top of my head what that call is. You have to take half that time because you would only want to find the distance one way, not the return. So you would use velocity equals distance over time. Velocity times time equals distance. 5 times 0.01, because half of that would be your distance. Whatever that happens to be. And again, this is a completely made up, nonsensical problem because it's just an example. So I'm hoping this helps. Make sure you study your parts. Make sure you study your wave behavior. I really do think that y'all can do this if you take a deep breath. Make sure you do your review. Email me if you have questions tonight.